So we'll move on to the next questions. So now once again, it's an insulating sphere and is uniformly charged. Okay. Calculate the charge enclosed by the concentric surface with a radius of r equal to 2.1. So what is happening here is that let's identify the given information. So we should so diameter of this sphere is given d, and this is the r, which is d over 2. And in comparison to the previous case, we had a Gaussian surface outside, but we are now trying to think about enclosed surface inside with the radius of r. Note that the radius sphere is 3.8 and radius the enclosed surface is 2.1, such that we are talking about sphere inside a charge distribution. Okay, so and once again, we are talking about uniformly distributed throughout the volume such that the charge density is constant, low. So that the charge density is given by the total charge divided by the total volume is V total. And then in this sphere of the radius small r, and the volume is given by 4 pi. Okay, and then what you can do is that the V total is, so let's try to think about this over. And if you think about Q charge enclosed is given by rho times volume enclosed, which is this one. And then if you do the calculation, you will get this formula. And then if you just plug in the numbers, you can get the outcome. And note that once again, it is R cubic, such that inside the uniform charge distribution here. So if you apply the Gaussian Gauss law, so that and then we note that here E is going to be uniform because of the uniform charge distribution. So it should be radial so that you get 8 times 4 pi small r square is given by 1 over epsilon naught here. Q times r cubic, or capital R cubic. Such that E is now proportional to r square, r is proportional to r. And then you remember that in this case of a electric field, it increases with the r and then decreases with the r square. Okay, so this is the case. The case is the capital R. Okay, so I just want you to remember this diagram as well. Now let's try to think about cube of side A. Okay, so that we have A is given by 5 centimeters. So we have x-axis, y-axis, and z-axis. And note that electric field is given by some weird number, but it is along the I, which means along the these directions. And it is changing with the X. Okay, so that's the, as X increases, it is going to increase. So calculate the magnitude of the total charge within the cube. Okay, so in this case, we have E is known, vector E is known, and then we have enclosed surface known, which rho is known. So enclosed surface integral is integral over this cubic. Okay, and then from this is going to be Q enclosed epsilon naught. Okay, so that we can find out Q enclosed. So let's erase this. So let's summarize what we do know. So we know this closed surface cubic dimensions, and we know what the electric field is. And what we need to do next is that do the calculation of uh, electric flux through this closed surface. It's nothing but this one. So note that E is a vector, and actually A is also a vector. And then it is given by E dot A is EA cosine theta, and the theta is reference to the x directions. So note that E is parallel to I, so that means it's parallel to the x-axis. So that anything E dot Y or is dot J K is 0. Okay, this is the I, this is I. In other words, x-axis, y-axis, x-axis, z-axis, they are orthogonal to each other. In other words, if you think about this is the normal vector, which is parallel to the k, and this normal vector parallel to the y. And at the bottom, also, this is the minus k, and side here, minus y. So this 1, 2, 3, 4 sides are always orthogonal to the electric field. So that's the thing. The only non-zero contribution will be this side and this side on the back. Okay. So once again, top, bottom, front, back is going to be 0 because it is orthogonal to each other. And left face and right face, we get the same area. And the E left is given by this one. Okay. And you'll find out. But the thing is that you need to understand x equal to 0. So it depends on the x here. So when x equal to 0 here, x equal to 0 and x equal to 5, and you have a different electric field. So note that x equal to 0 is the plane left, and then you'll say that if you plug in the x equal to 0, and it is 0. So that flux electric field is 0, such that the flux is 0 for that surface. And for the case of the right, and then we plug into the x equal to 5, yeah, and then you get this one. And then if you add all the flux, yeah, top, bottom, front, back, and left and right, and then you get this one. And this should be equal to this one, okay? So that charge is calculated from the electric flux times epsilon 0. Okay? And then that's your answer. And then let's try to think about what is going to happen here. So radius of the sphere is 8.4 meter, and location of the point is halfway between the center and the surface. Halfway between the center and the surface. So what we are trying to do is that, once again, it is inside a problem. And we are assuming that total charge Q is uniformly distributed inside this sphere of the radius R. In other words, Q is given by rho times 4 pi r cubic 3. Okay, so rho is a constant. And then what we have to do is that magnitude of electric field at the point halfway between the center of the sphere and its surface. So we want to find out halfway here, okay? So we want to find out how. And then once again, we are going to draw Gaussian surface inside, okay? That's the thing. So let's try to summarize what is going to happen. So the radius of a sphere, capital R, is given, total charge is given, location of point is given by this one, okay? And the relevant equation in theory is that Gauss' law for the uniformly charged sphere outside, if our observation point is outside here, so that we take the Gaussian surfaces like this, and then this whole charge is reduced to the point charge at the center, okay? Act like a point charge. And inside, the electric field is determined only by the charge enclosed within the radius R. So we have to think about the charge enclosed within this sphere, radius R, and then that's been already done in the previous examples. It's given by this one. And then electric field is given by this one. And then this is E times 4 pi R squared. And then this is proportional to R cubic, such that you will get the linearly proportional to R. Okay. And then we need to find out the electric field at this position specifically, and then plug in R equal to R over 2, and then you end up with this simple formula. We know what the Q is, we know what the capital R is, and then you can find out the electric field. And now we are going to change to the cylinder. Okay. So let's go back. Long cylinder has a uniform volume charge density. Find the magnitude of electric field in the interior. So it's inside cylinder. Okay. So we have a cylinder like this, and then inside we have a R. We have a Gaussian surface, which is also another cylinder. And then we are going to assume that electric field is like this. And then we are trying to get the surface integral for the electric field, and then try to find out the Q enclosed. Okay. So, sorry, I think that I have done something wrong. Okay, so let's go back. So volume charge density is given by this one. Radial distance, small r, is given by this one. And note that the radius is, actual cylinder radius is greater than our position. In other words, we are looking inside problem. And then the electric flux is given by this one. And then in this case, we have a electric field is always orthogonal to this. So the top and the bottom, your normal vector is orthogonal to the electric field. There is no contribution. So that only the side surface, which is 2 pi RL, is contributing to the electric flux. And then this is the electric flux, E times 2 pi RL. So note that we are going to assume that electric field is constant at this surface. Because if you think about it, it's a cylindrical symmetry. There is no reason it will depend on the certain angle, so that it should be all the same here. Okay, so that we are taking the E is a constant at R equal at 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 position R. Okay, and then enclosed charge is given by charge density times the enclosed volume. Enclosed volume is given by pi r square, the area times the L, the length. Okay, and then apply the Gauss law. You get the E times 2 pi R. This is going to be the charge enclosed, and once again it is going to be proportional to R. Okay, so you will get a similar result for the sphere, uniformly charged sphere and the uniformly charged cylinder. So you find out that the electric field inside is proportional to radial position R. Okay, and point problem 43. So here is the a little bit more complicated cases. Here is the situation. So what is happening here is that you have two surfaces. Outside surface with a plus charge, and then inside surface with a minus charge. And then at the center, there is a wire that carries positive charge. So in other words, if you just redraw it, plus charge, minus charge, and then there's a wire at the center, and then it is carrying plus charge. So note that the cylinders have equal and opposite charges per unit length. So outside and inside surface carries the same charges, but the opposite sign. Okay. And then along the common axis runs a wire with equal positive charge per unit length, so that we have a line charge at the center. So in other words, we have a cylindrical a shell, and then we have a wire. So it looks a little bit complicated, but applying the Gaussian law, you can solve this problem more systematically and then surprisingly easy. So we have a radius of inner circle, R1, radius of outer circle, R2, okay. Location of interest, our interest is R equal to 0.2, which is inside. Okay. This is the R. Okay, charge density of the wire is given by this one. Charge density of the cylinders is equal and opposite, like this. Okay. And applying the Gauss law, we have, if we use this inner surfaces as a Gaussian surface, that's all. And we found out that the enclosed charge is only from the wire. This is the enclosed charge, okay? This is the simple thing you need to notice, okay? Uh, and then you get this is the 2 pi L, that is the, and then you have a E, Q enclosed is lambda times L, and times L over epsilon naught, okay? And then you can get E is, well, how you correlate this one. The charge on the two cylinders do not contribute to the electric field inside, okay? So that's the key thing you need to keep in mind. So in this case, you get this relationship, what's that, this one. R goes to the denominator, right? Like this. And then if you just calculate this one, note that this lambda is center wire. Okay, so that's the only charge that is enclosed by these Gaussian surfaces. Okay, now the next problem is that so now our interest is 17.5 centimeters, which is outside. So in other words, we have this positive charge, negative charge, and then wire, positive charge, and then our region of interest is here, outside. And then once again, we have to take the cylinder of the radius R and then length of L. Okay. And then we need to understand the what you have to count on is that enclosed charge, enclosed charge. So in this case, enclosed charge includes positive charge outside, negative charge inside, and wire at the center. But note that the positive charge outside will cancel out with the negative charge inside. So plus minus equal. And then the only contribution is, once again, this charged wire. Okay. So that's the importance of this problem. So net charges is important. And net charge is given by wire plus inside, outside cylinder. And then this will cancel out. And then net charge is going to be the linear charge density at the center. And then it has one of our dependence. And then if you just plug in the numbers, and then you can get the electric field. Okay, that's it. And then I think that you understand, first of all, the difference between the chapter 5 and the chapter 6. Chapter 5 is you are given some line charges and some line charges or ring charges or surface charges. But what we need to do is that do the integral element by element for the given point of interest. But in the case of chapter 6, we are using the Gauss theorem such that each individual integral of the charge element dq is now changed into more simple surface integral. And then we have to calculate the flux, electric flux, and then it is directly related with the charge enclosed by these closed surfaces. Okay, and then from this, anything inside is now leads to the point charge. And then if we have a cylindrical configuration, you need to have a cylinder. And then if you have this kind of planar things, then you need to have a box. So in the Gauss theorem application, you need to know the symmetry and then take the proper Gaussian surfaces. And that's it. It's more simpler. Okay, so I just want you to compare chapter 5 and chapter 6. The goal is, for the given charge distribution, we want to find out the electric field. Okay. I think then I hope you understand the goal and the difference between the chapter 5 and the chapter 6. Thank you.